We continue now with Chapter 4, Motion in a Plane, or, as this is often referred to, motion in two dimensions. What we're going to be doing is you need to bring you to the realization that motion with constant acceleration in the plane can actually be treated as two independent motions in the x and the y directions. We're going to obtain expressions or equations for movement in a plane from the original equations of motion applicable to movement in a straight line. And we're going to also come with expressions for components and for velocity and the position coordinates of a projectile or an object moving in a two-dimensional plane. And finally, we're going to derive an expression for uniform circular acceleration, or what we call centripetal acceleration of an object. And of course, you're going to be solving problems on these concepts. To introduce this chapter, we refer to the example from the text where they say, a puck moves across a horizontal air hockey table at constant velocity in the x direction, as shown in figure A. So you can think of the hockey puck as just a metal disc which is moving on an air hockey table, and the air hockey table is essentially a frictionless surface. So we have a disc moving on a frictionless surface. It's moving with constant velocity, and we're representing the velocity by this arrow as shown. If you look down at the table from above, then you're looking down into the XY plane. And looking onto the table, you can notice that the hockey puck is just moving in the X direction. Then they say, for figure B, that refers to the case of after a puff of air in the y direction is applied to the puck has gained a y component of velocity, but the x component is unaffected by the force in the perpendicular direction. So this is to say that this puck, it's given a brief push by means of giving it a puff of air in the y direction, and this causes it no longer just to move along the x direction as shown in A, but now it's moving along at some angle, right, relative to the x-axis. And this is because now the puck, it has velocity components in two directions. It has the original component in the x direction, which is unaltered. See, it's the same in A as in B. But for B now, after that puff of air, it also has a velocity component in the y direction, which these little independent arrows pointing upward show. And then you realize that the motion in the xy plane in the two dimensions can be modeled as two independent motions perpendicular to each other. So as summarized in blue, we can, after the puff of air is applied, we can treat as two independent motions in both the x, these arrows here, and the y direction. Here's another example of motion in a plane, or motion in two dimensions, and this is an angry bird. So the angry bird is being shot off at some angle, and then it's following this projectile motion trajectory through space. In this case, we're viewing it from the side. Again, you can see its velocity is this arrow shown as a tangent at each point along the path, and it's made up of two components. It has an x component and it has a y component. We'll speak a little bit about this in more detail to come. We will be considering motion in a plane with constant acceleration. We will consider the acceleration to be constant in both magnitude and direction. A way for us to generally express the equation for the acceleration, this will be the overall acceleration vector, and it will have a component in the x direction, ax, in the I hat direction, plus a component in the y direction, represented by j hat. And these values themselves will be constants. We've seen that motion in a plane can be considered as the sum of two independent motions in the x and the y directions. And precisely for this reason, when we want to model the motion, we can employ our four equations of motion before and we employ them independently in each of the x and the y directions. So we have 4 equations relating to the x direction as indicated by the subscript x, and similarly another set of 4 equations that we apply to the y direction independently. Here's an example. A particle moves in the xy plane starting from the origin at t equal to 0 with an initial velocity having an x component of 20 meters per second and a y component of minus 15 meters per second. The particle experiences an acceleration in the x direction given by ax is equal to 4 meters per second. So we have some particle moving in a path in the xy plane, and we've been given its initial velocities component wise as well as acceleration. Then we've been asked to determine the total velocity vector as a function of time. If we look at the solution provided, you know, the information that we're given is ux equals to 20 meters per second, u in the y direction, the initial velocity in the y direction is minus 15 meters per second, and the velocity is changing, so the acceleration in the x direction is 4 meters per second squared, and ay is equal to 0. So to describe the velocity, we can make use of this equation because we're given the initial velocity and the acceleration, and we need to do it independently in both the x and the y direction. So if we apply this equation in the x direction, then we have u plus acceleration times t in the I hat, and if we apply it in the y direction, we have u, now it's minus 15, plus the acceleration, which is 0, in the j hat. So the general expression we come out with then is given by this here. Secondly, we're asked to calculate the velocity and the speed of the particle at t equals to 5 seconds and the angle the velocity makes with the x-axis. So for us to perform this calculation, we note that the expression that we've just derived for the velocity in general is this expression given here. You can see it depends on time, right? It's going to change with time. We have a t there. So in part B, we asked to calculate the velocity at t equals to 5 seconds. So for part B, what we do is we say at 5 seconds, we substitute in the value of time equals to 5 seconds into this equation. And then we come out with an expression for the final velocity of 40 meters in the I hat direction, minus 15 in the j hat direction. So calculate the velocity and the speed of the particle at t equals to 5 meters per second. So this is a general expression for the velocity that we've used to find the value after 5 meters per second. But if we ask to calculate the actual speed and the angle, then we need to realize that this is a vector, right? And we can accordingly draw it as a vector. So we've drawn the velocity vector. It's 40 in the I hat direction, so its x component is 40 and its y component is minus 15. And when it comes to finding the speed, we ask to calculate the length of this vector that represents the speed, and the angle is this angle shown in red. So you can for yourself go through this calculation whereby you calculate the angle using tan and you find it to be minus 21 degrees. So the minus 21 degrees means 21 degrees from the x-axis in the clockwise direction. Another way to say that would be 339 degrees. That would be fine as well. That's going in the clockwise direction. And the speed is the length of this vector, which is found using Pythagoras, and that is found to be 43 meters per second. So we consider now projectile motion, and when we speak of projectile motion, we're thinking, for example, of a bullet being shot by a tank, or a projectile being shot by a tank at some angle, perhaps someone standing on the top of a cliff throwing a stone off the cliff at some angle. We think of that Angry Bird example of the Angry Bird being shot out the catapults. And under the assumptions of projectile motion, we assume that gravity is the only force acting on the object. So we're going to ignore any effects like air resistance or rotation of the Earth. If we are to draw a force diagram of the forces acting on the object as the object travels through the air, then the forces acting on it will be, the only force will be the force of gravity, which is acting downwards. The force of gravity is, of course, a vector, and it's given by 9.8 in the minus j hat multiplied by the mass. So this is the force acting on the object. You'll remember we said for motion in 2 dimensions we can express the acceleration as this vector shown. So in this case, the x component of the acceleration is going to be 0. There are no forces acting in the x direction, so the x direction acceleration is 0. And in the y direction, the only force acting on the object is gravity, and ay is going to be 9.8 meters in magnitude. Of course, the sign is going to be negative because it's going to be in the negative j hat direction. So once again, if we look at the equations and what's going to be happening, it's critical to choose the origin of the axis where the motion begins. So we have the motion beginning at this point here, and we have something being shot out at an angle. You can see the angle is theta r. Perhaps this is a tank shooting a bullet or a projectile at this angle. It has some initial conditions. So the initial angle at which the projectile is launched is theta r. It has an initial velocity. This is called vxi in the x direction. It also has an initial velocity in the y direction, vyi. For us, we may also use the notation ux for the initial velocity in the x, or uy in the I direction. So the projectile is launched with the initial velocity v. This is important. If we add the x component and the y component of the velocities, we get this initial velocity, which is vector. After some time, this projectile heads along the path and it comes to point B, and you can see what's happened at point B. Well, the y component of the velocity has got slightly smaller. This is why. This is because gravity is acting on the object, pulling it downwards, slowing it downwards in the upward direction. So the y component of the velocity has got slightly smaller, whereas in the x direction this component stays the same. The reason for this is, as we just said, the acceleration in the x direction is 0, and this means that the velocity is going to remain the same. The object continues in this trajectory until it reaches the peak of its path. Here the y component of the velocity is 0. See, there's no y component, no arrow pointing upwards. So the y component is 0, and the resultant velocity is just going to be the x component. So in this case, vy is 0, and the final velocity is just this x component, or the resultant velocity. Then as the particle starts moving downwards, gravity is again pulling it downwards. So we have an increase in the y component vector. Again, it's pointing downwards now because the object is moving downwards, and this x component remains the same. again, when we add the two, we get this resultant tangent to the path. And at these points, let's see what they've written. They've said the x component of the velocity remains constant because there's no acceleration in the x direction. If we turn our attention to the initial component in the x direction and the initial x component of the velocity and the initial y component of the velocity, we can in fact find out what those are by making use of trigonometric functions. On the following slide, the initial component vxi is equal to vi cos of theta, and vyi is equal to vi sine of theta. So we can find the x and the y components of the initial velocity using cos and theta. Remember, it's as we did in the chapter on vectors. The x components follow cos, y components follow sine. For ease of notation, we may also, instead of a vxi, we may just call that v, or we may call this u. We may call this ux. We may call this component uy, and we may call the initial velocities u. That would be an alternative notation. So this summarizes what we have initially. Initially, we'll have some initial velocity component vector as the projectile shot, as the bullet is shot out the cannon, or the angry bird is shot out the catty. It shot it with some initial component vector u, and then we'll break that into the x and the y components as shown here, using the cos and the sine terms. And then once again, for distances, we'll be able to use the equations of motion. If we're interested in finding the y distance, then we use the distance y is equal to uyt plus half ayt squared, where these are these values given here. And we would know that the acceleration in the y direction is given by minus 9.8, which is simply the gravity. If we look in the x direction, in the other hand, then we have a similar equation of similar form, and here you can see ux is going to be u cos theta, and the acceleration in the x component is 0, so the second term is going to fall away. So take a look at these slides and familiarize yourself with the concept of breaking the vectors into their components and then applying them to the equations of motion. We'll see some further examples of that to come. In the next slide, we consider some interesting cases. We consider the projectile being shot out at different angles. You can see here the angle is 75 degrees, and we look and we see where does it land. And here you can see the angle can be changed to 60 degrees, 45 degrees, 30 degrees. And we note two interesting behaviors. First is that the maximum horizontal distance occurs for an angle of theta equals to 45 degrees. That's this line here. It has the longest path. It goes just over 250 meters. So this shows that if you want to throw a shot put and you want to throw it as far as possible, then the angle that you need to choose is 45 degrees to get that maximum distance. The second interesting point is that we note that for all angles other than 45, any two complementary angles will yield the same distance. By complementary angles, we mean any two angles that when added together give 90 degrees. They will give the same distance, the same range distance. For example, let's look at 75. 75 will land over here. If we look at 15, it lands at the same place, and we notice that 75 plus 15 is 90. Similarly, for 60 degrees will land over here. and 30 degrees also lands at the same point. Of course, 45 degrees plus 45 degrees is 90 degrees, and 45 gives the furthest. We take a look now at this example of a long jumper as shown in the figure. He leaves the ground at an angle of 20 degrees above the horizontal and a speed of 11 meters per second. And then we asked a number of different things about this long jumper. How long does it take him to reach his maximum height? How much time does he spend in the air in total? And how far does he jump in the horizontal direction? So in order for us to tackle this type of two-dimensional problem, we start with a drawing, and this is the information we've been given, that he launches at 20 meters, 20 degrees, and he has an initial speed of 11 meters per second. So as we've just seen with projectile motion, we can consider it in both the x direction and the y direction, and we need to consider these two directions independently. So if we need to list all the information known and the unknowns, we need to do that independently in both the x and the y directions. The different quantities which we need to know about is ux, it's ax, it's time, and it's sx. Sx refers to the distance at which the total distance which he would jump. So sx in this case would be this distance here shown in purple, sx, right? Similarly for y, we'll have a number of different quantities. The first quantity will be uy, the initial velocity in the y direction, and we'll be interested in the acceleration in the y direction. We'll be interested in the time, and we'll be interested in the distance in the y direction. The distance in the y direction is going to be this height that he reaches, the height. Okay, so we can begin to fill in some of the values. We've listed all the quantities, now we fill in the knowns. So we know that the x components of the initial velocity, this is going to be given by ux cos theta. So we can immediately see that this is going to be 11 cos of 20 degrees. And if you use your calculator, you can calculate that to be 10.34 meters per second. Similarly, something we can calculate is the y direction, the initial velocity of the y direction. This will be 11 cos 20 degrees. So this will be 11 sine 20 degrees. And if you calculate that out, then you'll see that is equal to 3.76 meters per second. So in this type of projectile motion calculation, we always split it into the x direction, split it into the y direction, and then first thing we do is calculate the x and the y components. The next thing we're able to do is, since it's projectile motion, we know information about the acceleration. The acceleration in the x direction is going to be 0. The reason for this is because there's no air friction, we're not taking any spinning of the earth into account, and so forth. The acceleration in the y direction, this is always minus 9.8 meters per second squared. So we're able to fill that in. The next quantity that we would like to know about is time. Well, we're not given any information about time in the question. We certainly know that these two will share the same time. So the values of time will be the same between the two equations. That's what links them together. We don't have any information about a distance, but in part C we asked to calculate how far does he jump in the horizontal direction. So Sx is actually what we've been asked to calculate. We're not given any information about Sy. Of course, the other quantity I forgot to mention is the velocity. So we also could have some information about the velocity. Well, certainly we know that once the person jumps and he reaches the top, then at the top his velocity is going to be 0. The y component of the velocity is going to be 0. So I can fill this in here. The y component of the velocity is equal to 0 at the top. That's another piece of information. Right, so let's take a look then at the questions and use the knowns and unknowns to solve the questions. For part A, we asked how far does it take him to reach his maximum height. So at the maximum height, we know Vy is going to be 0. And we also know, so we know Vy is going to be 0. We also know these quantities here. We know Uy and we know Ay. So these are the quantities that we know. So if we want to know how long it takes him to reach his maximum height, we can see knowing Uy, knowing Ay, knowing Vy, a good equation to use will be Vy is equal to Uy plus this will be a good equation to use because we already know three of the quantities. So then we can simply substitute in the values. We can say at the top we'll have 0 is equal to the initial is this value here is 3.76 minus the acceleration is minus 9.8. So it's minus 9.8 t. That's the expression. And then we can solve for t. And we're going to get t is equal to 3.76 over 9.8. This is going to be minus. This is going to be minus. The minus comes from taking that to the other side. And when we divide those two, then we get t is equal to 0. We get 0.3837 seconds. These signs will in fact be positive. We see when we take this t to that side and divide by the 9.8. The signs are positive, so as expected the sign of the time is positive, and this is going to be, just to remind ourselves, it's going to be at the top of the trajectory, the top of the jump. So this refers to this point over here at the top. So it means it takes him 0.3837 seconds to reach the top. In question B, we asked how much time does he spend in the air in total. Well, the time is going to be symmetrical. The time taken for him to reach the top will be the time taken for him to reach the bottom. So the total time then will be 2 times this. The total time will be 2 times 3 points. 0 points. 2 times 0. Let me just rewrite this. Be t equals 2 times 0.3837 seconds, and this is going to give us 0.7673 seconds. So that's the solution to B. For part C, we asked how far does he jump in the horizontal direction. So we know how long he spends in the air. The total time is 0.7673 seconds. If we want to know how far he jumps in the horizontal position, then we need to use an equation applying to the horizontal position. And the equation that we use is Sx, the distance traveled in the x direction, is equal to uxt plus half xt squared. If we look at the values that we have, ax is in fact 0. Because ax is 0, it means the second term is going to fall away. So we're going to have ux, which, uxt, so we're going to have 10.34 times the time is 0.76 plus half of 0 times t squared. So as I said, this term falls away, and 10.34 times 0.76 gives us this value of 7.94 meters. An interesting way to think about this problem is, perhaps you've heard of basketball players that jump in the air and then they use that term hang time. How much time can the person spend in the air? What is their hang time? So here we see the hang time of this person, the total time he was in the air is given by this 0.7673 seconds, and the whole time while he was in the air, he's moving at constant speed in the x direction. So his speed in the x direction is simply given by this x component here. So the total distance he travels is going to be his speed multiplied by the hang time, which then gives us this answer. Of course, the second term falling away because the acceleration in the x direction is 0. Here's a second example which is similar to the long jump example. It says a stone is thrown from the top of a building upward at an angle of 30 degrees with an initial speed of 20 meters per second, as shown in the figure. The height above which the stone is thrown is 45 meters above the ground. So we asked then to calculate how long does it take the stone to reach the ground. So again, you can solve this by making use of the figure and considering the x and the y motions separately. So take note, we put the axis where the motion started, and we have these two, the angle and the initial velocity. So the first thing we can do is calculate the initial velocity in the x direction. That will be u cos theta. We can calculate that to be 17.3, and we can calculate the initial velocity in the y direction using sine of theta, and this gives 10 meters per second. You can see both are positive because the stone is being thrown upwards. Then the equation, the equation that we're going to use to find out how long it takes for the stone to reach the ground is an equation of the form S is equal to ut plus half at squared. You need to take note for the distance s, also represented by this yf, we make use of minus 45 degrees. The reason why we use minus 45 degrees is because it's 45 degrees downward, it's below the origin. And then again, working in the y direction, the initial velocity in the y direction is going to be this component that we calculated of 10 meters per second, and the minus half at squared, we're using the acceleration as minus 9.8 meters per second, and then it comes out to be that we find the time that the stone spends in the air is 4.22 seconds. We could have been asked an additional question: how far does the stone land from the building? how far does the stone land from the building. If we were asked that, it would have been similar to part C of our previous problem, and we would have just used, the distance in the x direction is the initial velocity in the x direction multiplied by the time. We have those quantities here because we've calculated the initial velocity in the x direction, and we have here the time, so we would multiply those two together, and this half a x t squared term will just fall away, because remember, the acceleration in the x direction is also going to be 0 in this case, because it's a case of free fall. Right, so next topic we look at is uniform circular motion. From the name circular motion, you can understand that we're going to be dealing with something moving in a circle. The uniform part of the name refers to the fact that the speed isn't going to change. The speed is going to be uniform. It's moving with a constant speed. Some examples that provided here is a rock twirled in the circle on a string with constant length. That might be like someone using a slingshot, like David and Goliath. A planet moving in a perfectly circular orbit. Perhaps the planet is moving around, say, the sun in a perfectly circular orbit. A charged particle moving in a uniform magnetic field, or perhaps an electron orbiting a nucleus, moving in a circle around the nucleus. We've already seen that velocity can change either in magnitude or in direction to cause acceleration. So under this case, we have an object moving with constant speed in a circle, so the speed isn't changing, but the particle is accelerating because it's changing direction. The direction is changing the whole time. So the particle is said to undergo centripetal acceleration. And centripetal acceleration, like other accelerations, it's a vector, and it's a vector that points towards the center of the circle. We're going to, calculate an expression for the size of the centripetal acceleration, its magnitude next, but for now, be aware that it's a vector that always points towards the center of the circle. One interesting question for us to ponder is if the centripetal acceleration points towards the center of the circle, why doesn't the particle accelerate towards the center of the circle? Why does it remain in this circular trajectory? And the answer to that is, if the centripetal acceleration wasn't there, the particle would have moved in a tangent to the circle. So if for some reason suddenly the centripetal acceleration disappeared, the particle would continue moving in a straight line in a tangent to the circle. But by virtue of this centripetal acceleration, it acts towards the center. In essence, you can think of it as accelerating it towards the center, and the combination of the fact that it was traveling in a tangent and the fact that there is this centripetal acceleration, that's precisely what keeps it in this circular orbit, changing its path from keeping it in the tangent at each point. We have discussed how the direction of the centripetal acceleration is always towards the center of the circle, and we're also going to derive an expression for the centripetal acceleration for its magnitude. And the expression that we're going to derive is that the magnitude of the centripetal acceleration, AC, that's centripetal, it's given by v squared over r, where v is the speed of the particle and r is the radius of the circle in which it's moving. Before we come to that derivation, as part of the derivation, we're going to use the concept of similar triangles. And just to explain what that concept is, here we have a little triangle, and its one side is 1, a length 1. This other side is length 4, and between these two sides we have an angle of 110 degrees. The idea with similar triangles is that if you think of yourself and you think of your mom and your dad, you in some ways similar to them, right? So you're part of the same family. So in similar triangles, the idea is that we have a whole family of triangles that are similar. Let's draw a bigger brother version of this one. So in this bigger brother version triangle, this size over here is going to be 2. This angle is still going to be 110 degrees. And this angle side here is going to be 8. Right, this is our bigger triangle. These two are similar in the sense that this one, the second one, is sort of a magnified bigger version of the other one. You can see this side's length is twice the black triangle's length, and here we have a length which is twice the black triangle's length once again. You know, we could have an even bigger version of this triangle. An even bigger version might look like this, right? So this bigger version, it would still have 110 degrees, and it would have, in this case, its length might be 4 times the 4, and maybe this length is 16. So it differs by a magnification factor of 4. But by virtue of these triangles sharing the same attributes of side, angle, side, they're said to be similar. And the key property of the similar triangles that we're going to use in our derivation is if we look at the ratio of the small side over the big side, in this case we have a ratio of 1/4, and if we compare this to the similar triangle, here we have a ratio of a small side over a big side of 2/8, and 2/8 is actually also, you can simplify the fraction to also have it 1/4. If we look at the third triangle, in this case we have a ratio of the sides of 4/16, and 4/16 is of course also equal to 1/4. So the property of the similar triangles is such that the ratio of their appropriate sides are equal. Let's get back to our derivation. What we would like to show is that the magnitude of the centripetal acceleration is given by the speed squared divided by the radius of the circle in which the particle is moving. So what I have here is a figure, and this figure is, you know, the derivation is based on this figure. We have some maths that follows from this figure. Before we get to the actual maths, let's take a look at where the figure comes from. So in terms of the particle moving, we have the particle moving in a circle. Initially it would be at this point shown here, and remember we spoke about how the particle moves at some tangents to the circle. So if our particle is rotating clockwise, then at this time it's going to have a velocity vector which points in this direction. I'm going to call this velocity vector VI. Then it will have rotated clockwise around the circle, and at some time later, sometime t, it will find itself at this position here. And in this case, the velocity vector will now be pointing in this direction. It's a tangent to the circle at this point. The particle is shown as such. So this velocity, I'm going to call this VF. It's correct for us to place arrows above the VI and VF because they're vectors. We note that the speed of the particle isn't changing, only its direction is changing. So the length of the velocity vectors are the same, indicating that the speed is the same. You will remember that when we define acceleration, in general, acceleration is given by this expression. Acceleration is equal to VF minus VI. divided by the time that's elapsed, delta t. This is the general expression for acceleration. Some other quantities that we can fill in on the circle is, if this is the center of the circle, then we have a radius here. We say that the circle has radius r. This segment here is also going to be the radius. These both have lengths r. Another thing that's of interest to us is the displacement of the particle. If you remember, we spoke about displacement being a vector that points from the beginning position to the final position. So our particle started there and then it points in this direction. It's an arc that points like that. That's the displacement vector. I'm going to call this delta S. I'm going to say that during the time of rotation, it's changed position, but it's also rotated through some angle, and I'm going to call this angle delta theta. I'm using the delta because it's changed and the theta to represent an angle. So this is the schematic that represents what's happened. If you look at the definition of acceleration, it depends on Vf minus Vr. And we already have two vectors, Vf and Vr. But we need to somehow work with these two vectors to get vectors Vf minus Vr. So as the first step, what I'm going to note is that if you take the minus sign of a vector, it means that the vector is going to be the same length, but it's going to point in the opposite direction. So because of that, I can draw a vector like this, and this vector here is going to be minus v. Check it out. It has the same. It has the same orientation as VR, but it points in the opposite direction. So it's minus VR. I'm also going to move this vector here. I'm simply going to shift it upwards, and I'm going to redraw it in this position over here. So over here, I'm going to have vector VF. Just simply shifting it upwards, which is allowed. And if you note now, what we have is another vector. I'm going to introduce another vector, and this vector is going to be given by the vector sum of these two. It's going to be this vector plus this vector. So I can draw this new vector in. This new vector, I'm going to call this vector VF plus VR. You can see it's the sum of these two vectors. So this vector is going to be VF plus minus VR, so it's going to be minus VR, the sum of these two. And by definition, this vector is actually delta V. It's the change in velocity. So what we've done is we've created a vector which is the change in velocity, this green vector. Another important point we need to make use of in our diagram is the fact that here we have a cyclic quad. If you consider this point, this point, this point, and this point, it's a cyclic quad, right? And we know that if you have any quadrilateral figure, that the sum of the angles add up to 360 degrees for a quad. So let's take a look. This here forms a tangent, so we have this here angle being 90 degrees in our quad, and this angle here is also 90 degrees, and we said this angle here is theta. So now we're interested to know what this angle over here is. Well, this angle plus this angle plus this angle plus this angle must all add up to 360 degrees. This is already 90, this is already 90, so these two together add up to 180. It means that this one here must be 180 degrees minus theta, right? Because now we have 90 plus 90 is 180, then plus 180 minus theta will be 360 minus theta, plus delta theta will give 360. So this angle here is going to be 180 degrees minus theta. Because this forms a straight line, it means this angle shown here must be equal to delta theta. That ensures that the sum of these two angles is 180 degrees along the straight line. So this angle here is delta theta. So as I've shown now, we've able to produce the sketch that we're going to use for the rest of the derivation. So we've just seen how we have a sketch as shown here, and we've seen from this page, I've shown you the origin of the sketch. I've shown you every step in producing the different vectors, the different quantities of the sketch. And now what we're going to do is continue working with the sketch to derive this equation here for the centripetal acceleration. So the derivation says, consider a particle moving in a circle with radius r with constant speed, vi equals to vf equals to v. Because the speed is constant, it's unchanging, and we're just going to call it v. So we said our particle is moving in the circle. Now, the next step of the derivation refers to two triangles. The first it mentions is triangle AOB. That's this triangle here. And they say that it's similar to triangle CDE. So the two triangles are similar. And the reason for that is side angle side. So as we mentioned, this has side R and delta theta. This one is similar in the fact that it has side V. It also has an angle delta theta, and then it also has another side V. So these two triangles are similar. Because these two triangles are similar, we can take the ratios of delta S over R is equal to delta V over V. This is what we saw previously when we looked at what it means for triangles to be similar. You'll remember we were able to take ratios of different sides, and in each case the ratios were the same. So it's the same kind of idea. In this derivation, we're working with the two triangles, the one triangle here, the second triangle here, and we take in the ratio delta S over R in this triangle. It's going to be equal to delta V, that's this long side of this triangle, over V. That's where we get this expression from. So we can then rearrange this expression to say that delta V, we can make that the subject of the formula, and we have delta V is equal to V times delta S over R. From definition, the centripetal acceleration would be delta V over T. That would be from definition. That would be similar to what I wrote over here, right? And now what I do is I substitute in for this value delta V. I've already seen that delta V is given by this, so I substitute this into equation 2 for delta V. Sub in equation 1 into equation 2, we get the centripetal acceleration is V times this. We can simply rearrange this and have V over R times delta S over T. And the cool thing about this is that delta S over delta T is also V. So we have 1V over here. This quantity delta S over delta T is also V. So this gives another V. which gives a v squared over r. And there we've derived our expression for the centripetal acceleration. This slide simply shows the figure once again. Perhaps it's drawn a little bit bigger, a little bit clearer. So if you would like to, have a closer view of this figure, I simply provide it on the next slide. You can pause and make sure that on a piece of paper you're able to draw this figure from scratch using these steps that we followed. We have spoken about uniform circular motion, and now we continue to look further at the concepts of period and rotational speed. So it says, consider a particle that travels once around a circle of radius r in time t. So we're thinking about the time taken for a particle to move in one complete circle and return to its starting point. The circle has radius r. This time t for one complete cycle or one complete circle, this is known as the period. If we're interested to know what the rotational speed or the speed of the particle is, then we can use this formula. Speed is equal to distance divided by time. That's just a general formula. And the distance that the particle would travel would be the circumference of the circle, which is 2 pi r. The time that it takes is given by t. So here we have an expression for the rotational speed or the linear speed in terms of the period. We can also rearrange this equation if we would like to know what the period is, if we're given, for example, the rotational speed of the particle. We now conclude this chapter by looking at an example. A tire 0.5 meters in radius rotates at a constant rate of 200 revolutions per minute. Find the speed and acceleration of a small stone lodged in the tread of the tire, on the outer edge of the tire. Here's a diagram representing the problem. We have the tire, radius half a meter, and a stone that's traveling in a circle. We need to take note that not all the quantities are in SI units. We're given a frequency of revolutions per minute. We need to change this to revolutions per second. So we do that conversion by dividing the 200 by 60 seconds, since there's 60 seconds in 1 minute, which gives a frequency of 3,33 per second, revolutions per second. You will remember that previously we saw this expression for the velocity in terms of the radius and the period. You also remember that 1 over period is equal to 1 over capital T is equal to frequency. 1 over the frequency is equal to the period, and vice versa. So this means that we can rewrite this equation as shown here. What I've done is I've replaced the capital T, 1 over T, by frequency. Knowing then that the frequency is given by 3,33, we can substitute in the values, and we found out that the speed is then 10.5 meters per second. The second challenge that we're given is to calculate the acceleration of the pebble. In order for us to calculate the acceleration of the pebble, what we do is we make use of acceleration is equal to v squared over r, this expression shown here. We've just found that the speed is 10.5 meters per second. We're given the radius, and then we're able to calculate the size of the centripetal acceleration is 219 meters per second squared. Of course, we're dealing with centripetal acceleration, and its direction is always towards the center of the circle. So it's important that we specify that when given the answer to a vector problem. Well then, this concludes this chapter on uniform circular motion.